Okay, uh, they're giving us some information about this triangle, and they're asking us to find something else. So they're telling us AD is 26, right? So they're telling us that this blue segment, whoops, blue segment is 26, and they're telling us that BD is 10.4, and they're asking us to find EC. We'll call that X. And this goes back to those special properties of right triangles that happen if we drop an altitude down to the hypotenuse of a right triangle. And essentially, if we do that, right, we take this big right triangle and we create two smaller ones that are similar to it. But what we're interested in are those geometric mean relationships that come out of that. Okay? And we had two geometric mean situations that helped us out here. What's the one that's going to apply here? Which one of those three segments, blue, red, or green, is the one that can act like a geometric mean? Red, yeah. Because the altitude of the big right triangle, there's only two parts of that big right triangle that could be geometric means. Real quick, let's just review what those are. So if I have this big right triangle and I drop down this altitude, what are the parts of that right triangle that could be geometric means? Well, you told me the altitude is one. That's right. What else? Okay, the legs, right? Meaning these guys over here. It could be that leg or it could be that leg. But any one of those three segments could act as a geometric mean, right? In this case, it's the altitude. Remember how we write these things down. What do we want to do first when we're trying to write down our proportion? Where do we start when we're writing out this proportion to solve for x? Okay, I could make a template. And which parts of that am I going to fill in first? 10.4, yeah, right. When that's the geometric mean. We start with that because it occurs twice. It fills in two of the blanks. Where's the geometric mean go in this proportion? Let's put that away. Where's the geometric mean go in this proportion? Where do I put it? Okay, top on one side, bottom on the other. So it just has to go opposite, right? Opposite extreme. So there and there, for example, right? Start with the geometric mean. Now we got to answer the question. The 10.4, the altitude, is the geometric mean of what two things? Yeah, in this case, 26 in x, right? Because the altitude, if we look at this picture again, the altitude is always going to be the geometric mean of the two pieces of the hypotenuse that it cuts when we drop it down, right? So it's going to cut this hypotenuse into the pieces there and there, right? And so the red is the geometric middle of the blue and the green, right? So that's what an altitude does. Now, what about the legs? If I look at the legs, compare what happens with the legs. Are the legs, what are bigger in this right triangle? The legs or the altitude? The legs have to be a little bit longer, don't they? The altitude is going to be the shortest of those three things, right? So if I take one of the legs, for example, the leg is going to have to be the geometric mean of some stuff that's a little bigger than this stuff, right? So the red leg is the geometric mean of what two things? Okay, so it's going to be the whole hypotenuse, right? And, okay, good, and the piece that's closest to it. Right? When we drop down that altitude, remember it's cutting it into two pieces. We're just going to take the piece that's next to the leg and then the whole hypotenuse. Now that makes sense compared to what we did over here, right? Because we had to have the red leg is bigger than the altitude, and so it needs to be the middle of bigger numbers, right? So we get the blue one just like before, but instead of that little green one, we get the whole thing. Make sense? Okay, and what if we had done, say, this leg? Well, same rules apply. This leg is going to be the geometric mean of the whole thing and that little piece. Right? Make sense? Okay, so going back to our problem here then, 10.4, the altitude's got to be the geometric mean of the blue and the green. So if we plug those in, and x, and then how would we solve for x? Yeah, we just cross multiply, right? Just cross multiply and divide. So I get, if I do that math, I just get 26x equals 10.4 times 10.4, whatever that is. We'll just call it 10.4 squared, how about? Okay. And so what do I do to solve for x? Just divide by 26, and whatever I get, when I take 10.4 squared divided by 26, that's x. Right? Okay, good. All right, moving on. What about one of these guys? Same kind of problem. Only this time they're giving us CD. Okay, they're telling us that CD is 19. BC is 28.5. And it's asking us to find this whole thing. So you've got to stare it down for a second and see if you can come up with a geometric mean relationship. So, let's see if we can write them. Oh, Cheyenne, you're on the spot here. What do you think? Can you think of one of those that might be a geometric mean?
Would it be like 28.5?
Good. This is geometric mean, right? Good. So here's the geometric mean. Very good. Because it's a leg. It could have only been one of the two legs or the altitude. That's it. Okay. So how am I going to set up my proportion then? Let's see, Lindsay, if I set up my proportion, right, I can always start off by writing it like that. Where am I going to put? What do I start with? Good. So 28.5, 28.5. Very good, very good. And let's see, Hannah, what are the other two? What do you think? What else do we fill in the blanks with? Good. Okay, because we know that the leg is the geometric mean of the piece of the hypotenuse that's next to it and the whole hypotenuse, right? So we can just go like that. And we probably have to do more. From there, it's pretty trivial. You get that so much practice solving those. What do? Cross multiply and divide. Solve for x, right? No big deal. Now, what if, let's just change this one ever so slightly here. Let's say instead, what if they gave us CD was 19, BC was, let's say, we'll leave it the same, 28.5, and they wanted us to find AD. Call that x. That's just a little tricky. Yes. Yeah, you could. You're right. You could. So Amanda had a good suggestion. This is a big right triangle, isn't it? And so how would we solve for the whole thing? Okay, we could. We could. Well, I thought you meant something different. Okay, let's do it with the geometric mean first. So let's fill in the blanks here. So, okay, so what's the geometric mean? 28.5, just like before, right? That part stays the same. Now, the geometric mean, 28.5, is the geometric mean of what two things? Okay, so we got 19, right? The green piece. And then we need the whole thing, don't we? Right? So it'd be the whole thing. Let's make that orange. From there over to there is how big? X plus 19. So I can put that right there. Okay, make sense? That's a little tougher, but it's still not horrible. If I cross multiply then, you see what I'm going to get? What's 19 times x plus 19? I mean, that's going to look like this, isn't it? 19 times the quantity, x plus 19, because I'm multiplying this whole thing by that whole thing in that cross product, right? And that just equals 28.5 squared. So what would I have to do to solve for x? I could distribute if I wanted to. That'd be fine. Or I could just divide by 19. Take your pick. You see I have a choice here. I could distribute, or I could just divide both sides by 19 to cancel that, and then subtract 19 from that whole thing. Take your pick. It doesn't really matter. What if we do it the other way? That seems like that's the way that most people would think about it. If I distribute 19x plus, 19 squared, whatever that is, equals 28.5 squared. So now, what are the two steps I would do to get the x by itself? I've just got big numbers. I'm not going to write them out. But 19 squared is just some big number. 389 or something. No, more than that. 381. What is it? Okay, I'm going to subtract 19 squared. So 19x equals whatever 28.5 squared is minus whatever 19 squared is. All divided by 19. I could just plug that in the calculator and find out. Okay. Now, I thought somebody had something else going on here. There's maybe another way we could do this one too. We don't even actually, if that last problem I gave you, I guess I don't want to get rid of that. If I just go clear back here. I'm not saying this is any easier. In fact, it's probably a little harder. But how could you do this problem? Maybe without even having to use a geometric mean. Actually, you know what? That'd be pretty hard. Never mind. I thought somebody had another idea, suggestion. Oh, never mind. No, you can't really. Can't. If that, no, you can't. Never mind. Yeah, we could fill in some blanks, but it's way more trouble than it's worth. So that's clearly the easiest way to do that is with the geometric mean the way we did. Okay, so let's see next. Okay, how about these? These seem to be causing a few issues. These guys. These are tricky. Okay, so what about this? If they're giving me this information about a triangle, and we got to pick the values of AC that are going to make that happen, right? What's this one supposed to be? It's supposed to be, if you read clear over, it's supposed to be acute. Okay, so it's supposed to be acute. So how do we go about these now? I think these are kind of tough. They give us a bunch of information about this triangle. If I want it to be acute is, what kind of triangle would I nudge just a little bit to make an acute triangle? A right triangle, right? A right triangle is the boundary between acute and obtuse triangles. And so we're going to start off with, we always want to start off with a right triangle to begin with. And we're going to assume that we're starting off with a right triangle, and then we'll see how we could change AC to turn this from a right triangle into an acute triangle. So we got to know what's going to be the biggest side of this triangle. It tells us AB is 16, BC is 20, and AC, it tells us, and this is important, AC has to be less than AB, so it's less than 16. So what's the longest side? BC. Okay, so we know we can call that B and that C, right? And this side is going to be 20. Okay, this is A, and we know AB is 16. And so AC is what we're trying to find. Let's make that orange for the rubber band. We'll call that X. Right? So if it's a right triangle, we can pretty easily figure out what the value of X is. How? How could I solve to know how big this is when it's a right triangle? A squared plus B squared is C squared, Pythagorean theorem. So if I set that up, what squared, in this case, what squared plus what squared equals what squared? Okay, so leg squared plus leg squared equals hypotenuse squared, right? So x squared plus 16 squared equals 20 squared, right? How do I solve for x? What do I do? We can turn these into numbers. So x squared plus 256 equals 400. How do I solve for x? What do I do first? Subtract. So if I subtract 256, I get x squared equals 144. Now what? Square root. So x equals the square root of 144. So x equals 12. Okay, so we know the value that the rubber band, we know how much it's stretched if it's a right triangle. Now the question is, if we want to make this an acute triangle, are we going to stretch the rubber band or allow it to shrink a little bit if we want to make it acute? If we shrink the rubber band, this is my hinge up here. Isn't that going to pull this side down and make this thing obtuse? It's hard to see that. It's really easy. If the hypotenuse is the rubber band, it's pretty easy. If the rubber band were the hypotenuse, we would just shorten it to make this angle less than 90, right? Here's kind of a good rule of thumb, because these are tricky. If the rubber band is not the hypotenuse, they're tricky, but they're always the opposite of what the case would be if the rubber band were the hypotenuse. So if the rubber band were the hypotenuse, wouldn't you agree we'd want to shrink the rubber band to make that angle smaller? So you know it's going to be the opposite. You're going to stretch it. And if I do stretch it, you can kind of draw yourself a picture that would make sense. If I stretch that, I'm going to get 16 and 20 and something bigger than 12, like say 15, right? And then that's going to make that angle a little bit smaller, isn't it? See what I'm saying? If you draw kind of an exaggerated picture, you can sort of convince yourself of that. But it's almost easier just to remember it's the opposite of what the behavior of the hypotenuse would be. So we know we got to make it smaller, right? And so if we go back, what we're trying to do is fill in the blanks here, right? So we know it's got to be less than, well, actually greater than 12, doesn't it? We got to stretch this thing out, not shrink it. We shrink the hypotenuse, so we stretch this. So AC is bigger than 12 and less than what? Well, let's see. It tells us up here that AC has to be less than AB. What's AB? 16. Okay. So that's my upper answer. Now, what if it didn't tell me that, though? What if it didn't tell me that? What if it could be, that makes the problem a little easier, but what if we didn't have that condition? What's the other thing we always have to keep in mind here? I can make AC pretty big, but at some point it gets too big. what's the relationship in any triangle between the two shorter sides and the one longer side? It always has to be true. Okay, because the two shorter sides always have to be a little bit bigger than the one big side, right? So I could make AC pretty big, but when AC got to 36, then it's no longer a triangle, because the other two shorter sides wouldn't make a triangle when they touch. It'd have to be less than 16 plus 20 is 36, so it'd have to be less than 36 in that case. Make sense? Because our picture would look like this. If this was 16 and this was 20, so there's my two sides. If the other side was 36, it's not even a triangle anymore. It's just a line segment. Right? This would have to be a little bit less than 36 so that there could be a little bit of an angle in that thing. Say 35 and 16 and 20. Right? Make sense? That's that triangle inequality that we met a long time ago. Okay, so those are a little tricky. They are a little tricky. I'll grant you. Okay, how would we do? Got one of these. What if you just have to choose? It gives you three side lengths and you just have to choose one of those four. Okay, how would it be? How would I go about this? What do I have to do first here, probably? Say it again. Okay, yeah, I got to know which is the biggest side, right? Because that's the one that would be the hypotenuse if it's a right triangle. Well, let's see. 2 squared is 4. 3 squared is. So both of those are going to be smaller than the square root of 29, aren't they? So that's the big one. Okay. So then the question is, what's this going to be? Well, the square root of 29. What's the square root of 25? 5. Well, this isn't going to work, is it? Right? Because the square root of 29 is bigger than 2 plus 3. Right? The square root of 29 is roughly equal to, I don't know what it's going to be, 5.3, something like that, 5.3, 5.4, roughly. And so look at my triangle. I'm going to have one side that's 2, one side that's 3, and then I've got this other side that's too long for them to connect to, right? It's too big. So what's the answer to this one? Not a triangle. Impossible. Okay, that one doesn't work. Okay, let's pick one that's a little different. How about that guy? So 13 is the longest, right? I have to figure out what the hypotenuse would be for 5 and 12. So if that's 5 and that's 12 and that's x, what happens if x is a number that's bigger than 13? If the hypotenuse that goes with 5 and 12 is a number bigger than 13, then what does that make this triangle? Acute, doesn't it? Because the big side wasn't long enough to be a hypotenuse. What if this side is a number, what if this side were like 12.5? What if it's a number that's less than 13? Then this side is too big for the hypotenuse, which makes it obtuse, right? That makes sense? But if we solve this, x squared equals 5 squared plus 12 squared, look what we get. X squared equals 25 plus 144, so x squared equals 169. What's the square root of 169? 13, yeah. So what is this case then? It's a right triangle, yeah. 13, the long side exactly matches the length it would need to be a hypotenuse, right? Okay, good. We're getting pretty close to being done. I think that's... okay. The last ones, I'm almost tempted to not mess with these because we've done so many of these. The 30, 60, 90 and the 45, 45, 90s. Are you okay with those special numbers?
Yeah.
Okay. All right. Let's go ahead and head down. We got 15 minutes. Let's head down.